We're going to start the recording. All right, so the recording has started. All right, so a few more problems from section 8.1, sequences. Let me give you a moment to copy those down, those two sequences. Okay. So the first sequence is 3 minus 0.2 to the nth power. 3 minus 0.2 to the nth power. So the question, the question is here, the question is, what does this 0.2 to the nth power do as n gets large? Okay, well, we can incidentally, sometimes it's sort of fun to put the sequence in the calculator just to sort of, study how it behaves. So let me go ahead here and bring up the TI 8483 calculator, Smart View on the computer here. All right, so, and let me know if hopefully, if I'm going too fast, let me know. I think you had time to copy the examples. You're good on that? All right, let me share application. Yeah. Okay, so 3 minus, so of course what we do is, as you know, if you go to mode, you can go down here and put the calculator in sequence mode. Okay, you can put the calculator in sequence mode. And when it's in sequence mode, it allows you to type in sequences in the calculator. So you should have this on your TI 8384 calculator as well. Then when you go to y equals, okay, the minimum starting value is 1. So n goes 1, 2, 3, 4 up to infinity. N takes on integers, but the starting value of n is usually 1. And what I'm going to do is I'm going to type in my sequence. Okay, I'm going to type in my sequence here. And of course, I hit the X, that puts it in n. And that's my sequence. And then I'm going to go to window. I'm going to go to window. So this sequence, I'm going to take it out to 10 values of the sequence. Okay, so n max is 10. X min, I'll go from 0 to 10. I like that to match the n max. X scale will be 1. That way I'm showing every value for every integer. And maybe I'll do -5 to 5 here. Okay. All right, and I think, let me just look at the graph here. Let me just click on graph. Okay, and this is what I'm getting. One moment, let me move the phone out of the room here. So we'll just have to let that ring. All right, so this is the sequence. And let me see here. If I click trace, okay, if I click trace, and let me know if you're, and hopefully you're all following, let me know if you have any trouble. Hit trace, okay, so when n is 1, you get a value of 2.8. Well, that makes sense, because 3 minus 0.2 to the first power is 3 minus 0.2, that's 2.8. Okay, 3 minus 0.2 squared is 2.96. 3 minus 0.2 cubed is 2.992. And we keep going, So, I mean, I'm out here at the nth term. 3 minus 0.2 to the 10th power is 2.99999. So what does it seem to be that this sequence is approaching? What does it seem to be? That's right, John. That's right, Robin. 3. It's approaching 3. So the sequence appears to be converging to the value of 3. Okay, so now we can go to the actual problem here. Hold on here. And sort of, you know, we can more formally show it, but the first terms of the sequence, if we write out the first terms, like we mentioned, it's 3 minus 0.2 to the first, 3 minus 0.2 squared, 3 minus 0.2 cubed. Okay. And these are the 3 values of the sequence. The sequence appears to converge to 3. Okay, let me get that a little smaller. In fact, if you take the limit of 3 minus 0.2 to the nth power and let n go to infinity, this term here goes to 0. If you take it's a 0.2 is a fifth, right? So if you take like 0.2 squared is a fifth of a fifth. That's 1/25th. Well, let me let you copy it down. Hold on. Let me just give you a moment here. Okay, notice in the notation, I keep the limit there. I want you to do that for your next exam. That notation is important. Sometimes I think students don't use correct notation, not because they're maybe, I don't think they're lazy. I think they just maybe are a little scared to put the notation there. Maybe they're not quite comfortable with it. But I want you to become comfortable with the problems, and part of that is using the correct notation. So, okay. Now, the fact that this sequence converges to 3 means that this 0.2 to the nth power has to converge to 0. It has to go to 0. Well, 0.2 is, how can we sort of think of this in intuitive terms? Well, 0.2, I got to get this to show right. 0.2 is a fifth, right? So say n is 2. You'd have a fifth times a fifth. That's 1/25th. When n is 3, you're going to have a fifth times a fifth times a fifth. That's 1/125. When n is 4, that term right here is going to be a fifth times a fifth times a fifth times a fifth. That's 1/625. Clearly, that term is approaching 0 as n gets large. So, hence the sequence goes to 3. This is a sequence sometimes students have a little trouble with. oddly enough. But at any rate, I hope I've helped you with it. Are there any questions on that particular sequence? Okay, let's go to the next one. Okay, so here we have that the sequence, the nth term, is 2 times the square root of n times sine of pi over root n. So what might be a good way to approach this problem? What might be, helpful to sort of, what might be helpful to first do with the sequence? That's right, John. That's right. Very good. Graph it. Let's graph that sequence. So, okay, I'm going to go into the calculator here. And let me see, it's 2 times the, let's see, the square root of n. Oh, wait, hold on. Hold on. Let me stop the sharing here on this. Let me go back into the application. Right, okay, so now I'm back in the sequence mode. 2 times the square root of n times the sine. Whoops, I just screwed that up. Hold on, let's try it again. 2 times the square root of n times the sine of pi divided by square root of n. Okay. All right. And type that in. I'm letting n equal 1. Starting at n min starts at 1. Let me check my mode again. Let me make sure my calculator, yeah, it's in radians. Okay, that's good. Let me go to window. So I'll go from 1 to 10. I'm unsure what this is going to do. So for my window, maybe I'll have it go from, well, no, x min I start at 0. I always like the origin to be in my graph, but I'm gonna stick with these same values here. Okay, I'm gonna stick with all the x min, x max, and x scale, y min, y max, y scale. I'm gonna keep them the same as you see them. And let's do a graph. Okay, all right, so all right, let me change the window because I have a lot of wasted real estate down here. I don't need that that space below the x-axis. So if for y min, let me make it 0 here. And looks like the action's happening above, so maybe I'll make y max be 10. And let's see. Why don't I graph 30 terms of the sequence? I'm going to graph 30 terms. Okay, and so that means then that x max should go to 30. Okay, if I want to see every value of the sequence. So, all right, I'm plotting 30 terms of the sequence. Let's hit graph. Okay, that's pretty good. That's pretty good. Are there any questions so far? Are there any questions so far? Okay. Well, let me go to trace. And let me just move along here. A moment here. I don't know. I don't know if this is, I mean, I'm not getting, like, I'm looking at these like this. I go out to the 26th, 27th, 28th terms of the sequence. The values are not settling down, I mean, they're slowing down, but I'm getting 5.877, 5.89, 5.9. I'm not like, the values aren't settling down enough for me. So I'm going to go back to window. This time I'm going to do 100 terms of this sequence, 100 terms. X max will go from 0 to 100. No, in the window for the X, I'll go from X min to 0, X max to 100 with the next scale of 10. It's just like graphing a function. You have to have a reasonable window if you want to see the entire function. Well, I want to see the entire sequence. So, all right, I'll use this. Let's see, let me do a graph. Okay, that's good. Let me just see one thing here. Let me go to my mode real quick. Yeah, in terms of dots here, maybe I can have thin dot. Okay, maybe I can have thin dot here. One moment. Oh, hello. Hello, come on in. Yep. All right, and let's see if that just makes the graph a little nicer. So I'm picking thin dot. No, I don't like that either. Let me go back to mode here. No, let me pick dot thin. Let me try this dot thin here. Dot thin. Let's see if that. I'm just trying to make the dots show a little nicer on the graph here. Okay, that's good. That's good. Okay. So let me do a trace here, and let me keep going here and see. All right, it's still not settling down. All right, I'm gonna do one more try. Okay, I'm gonna do one more try. Go back to window here, and this time I'm gonna do 500. I'm gonna do 500. I'm gonna plot 500 values of the sequence. X max is 500, and X scale will be 100. Okay. So you see, I'm just doing what just doing what a student would do, right? You just have to play around with things a little bit. All right, let's try the graph there. All right, so the thin dot, let me see, was my thin dot on there? Yeah, it's on. So it only can do so much, the thin dot. But if I go to trace, and just move it along here. So now I'm past 100. This is the 105th value of the sequence. That's 6.18. Keep going. All right. And it's still not quite settling down, but it looks to me like around 6.26, 6.27, something like that, for the sequence converging. But the thing is, if you put that in WebAssign, it's not going to accept that answer because WebAssign wants the exact answer. But at least we know that the sequence is settling down around 6.2 something. All right. How many find plotting the sequence to be intuitively helpful? How many find that to be intuitively helpful? Okay, good. Thank you, John. Thank you, Tyree. All right. Thank you, Francesca. Excellent, excellent. All right, well, let's go ahead and look at the solution. Okay. So notice if you look at this, what is the this second sequence here? You have the square root of n, and you have the sine of pi over root n. What is the square root of n approach as n gets large? What is that approach? Who can tell me? Because when we're looking for a convergence of the sequence, we're trying to compute the limit as n goes to infinity. So you have the product of a square root of n and the sine of pi over root n. What's the first factor square root of n approach as n gets large? Who can tell me? That's right, Tyreek. You have infinity here times, and what about pi over root n? What's pi over root n approach as n gets large? What is this angle approach for large n? That's right, Robin, 0. And so the sine of 0 approach is then 0. So you have an indeterminate form, infinity times 0 here. Oh, we've seen indeterminate forms like that. What do we use to help us handle indeterminate forms? What special rule? That's right, Marvelous. L'Hopital's rule. Very good. All right, so what we'll do is we'll look at the limit of 2 times the square root of x times the sine of pi over root x. When we use L'Hopital's rule, we use it for functions of x, but then we can take the result and apply it to our sequence. So, of course, the 2 we factor out here. Okay, you can factor constants out in front of the limit, and then you'll have x to the half to the sine of pi times x over x to the half. But then I rewrite it. Just like you did in the exam in your homework. You had a problem like this. You rewrite it. Certainly in the homework you've seen this, and you're going to use L'Hopital's rule on this because you have 0 over 0. You use the L'Hopital's rule, and what happens is you get some simplification here. And you notice how I show the work. I show the chain rule being done. You need to do that also when you do your problems, on your exam. I want to see the work. Okay. So if I know that occasionally students will use a solution in the book, or in the key to help them understand the problem, and that's fine. But remember, the solution often leaves out important steps. The solution is a guide to the problem and gives you enough to understand. The solutions and the key are enough to help you understand how the problem is being solved. But oftentimes there's work left out, and I want you to show that work for your exam. All right, so now, whoops. Now, we're going to get then, as x goes to infinity, pi over x to the half is 0. The cosine of 0 is, cosine of 0 is 1, and you get 2 pi. So the sequence converges to 2 pi, which incidentally is approximately what? 2 times pi is approximately equal to what decimal? Give me a decimal rounded to 6.28. That's right, Robin. That's approximately equal to 6.28. Now, WebAssign won't accept 6.28 as an answer, but the fact that you got this result, that 2 pi, and that jives with your what you observed when you graphed your sequence is it's encouraging, right? So our sequence converges to 2 pi. All right, are there any questions on that? Okay, all right, no questions. Well, very good, very good. Well then, I'm going to stop the recording on this problem, and